When we start to discuss analytical chemistry, we'll have to talk about some of the vocabulary or terms that analytical chemists use. So, one of the most important ones would be the analyte. The analyte is the compound of interest that we're trying to measure, or the component. Could be a chloride ion, could be lead, could be a protein, any kind of compound that we're interested in knowing how much of it is there, or if it's detectable, depending on the goal of our analysis. And then we also have the matrix, and the matrix is everything else in our sample. A lot of times the matrix is water with perhaps some other components in it that could affect the analysis. Sometimes the matrix is more complicated, like blood. Blood would have a lot of proteins and other confounding variables in it that we may have to tailor our analysis to account for. Now, we do analyses to make determinations, and we use measurements to do that. So we often use those terms sometimes interchangeably, but some people like to define them a little bit more strictly. Next, we can talk about techniques. A technique is a chemical or physical principle that we can use to study an analyte. One of those principles could be that this chemical is an acid, and therefore it would react with a base. We may be able to use this to determine the concentration of it through perhaps a titration. A physical principle would be something like the color of the chemical. Say we have something that absorbs blue light. We could use this principle to determine the concentration using spectroscopy. And spectroscopy would be a particular technique. Techniques can include things like titrations, like I said for the chemical one, or a gravimetric analysis, or it could be something more complicated like atomic absorption, which uses the atomization of the sample, which is more of a chemical technique, but then passes that sample through a flame to very finely break it apart, shines light through it, and measures the absorption of that light. So it's also a physical principle. So techniques can employ both chemical and physical principles at the same time. And they can be applied to many different types of samples or many different analytes. For example, atomic absorption can be used to analyze many different metals in a sample, especially sodium and potassium and some of the other transition metal elements that you can add to that. A method is when we take a technique and apply it to a specific analyte in a specific matrix. So, if we have some analyte that we would like to measure, and say we have titration as our technique that we would like to use, and perhaps we want to measure the concentration of calcium in a sample, well, then we could use an Edta titration to do that. The Edta is the titrant, and it will react with the calcium, and that would be applying a particular technique for a specific analyte. And we will know the concentrations of the titrant that we would like to use, how much of our sample we should use, whether we should prepare the sample because perhaps there's a component inside the matrix that would interfere or cause us problems with the analysis. All of these things are important when you develop a method. Now, getting a little further down into the granular is a procedure, which is when we apply a particular method to an actual sample. So we take the method and we say, you must do this to actually conduct the analysis. So things like, I'm going to dilute this 10 times its original concentration, and then I'm going to take 5 milliliters of it and perform the analysis on that. Things like that would go into a procedure, but they would not be as important in a method. A method will just let you know, I would do the certain steps in a certain order, but a procedure is a little bit more detailed. And then we can even go down to protocols. Now, protocols are very, very specified, so that they're very strict, so that a particular analysis will give a certain result that would comply with a law or a regulation. These are often written by federal agencies, such as the Environmental Protection Agency, like EPA, or the Food and Drug Administration, FDA, for particular analysis. And those procedures are very strict so that they comply with the regulations. So these are protocols. It's really actually just a procedure that's very well described, and you must follow it exactly. They even often include how to calculate and your answers and how to report the data, what kind of units they want. Everything is generally specified with that. Now, finally, we're going to talk about signal. The signal is the chemical or physical property that's proportional to the amount of analyte. So, in the case of a titration, this would be the volume of titrant. The volume of titrant would be the signal. In a UV-vis absorption measurement, it would be either the percent transmittance or the absorption, the absorbance would be the signal. Sometimes it's a voltage, sometimes it's a current. Anything that we're measuring that is proportional to the amount of analyte. It could even just be the readout on a balance, which ultimately is related to either a voltage or a current if you're talking about an electronic balance, but I digress. Signal is what we're actually measuring. So these are some of the terms that we'll be using in analytical chemistry when we describe various methods and techniques. We'll mention dealing with different matrices, how we evaluate these procedures. All of these things are going to be important. And we'll also study how particular analytes can be determined, and this will all come into play during this course.